Okay, this is the third lesson in chapter 13, and we are still in section 13.2. What we're going to be looking at today, though, is how much heat it takes not just to melt or boil something, but how much heat it takes to change the temperature of something, of some particular substance. And then we're going to combine the two parts of this lesson together. So let me put up here, if you remember, I hope you do, if I take and put heat in, and this is heat going in at a constant rate. So if I was to mark this, if this was 100 joules, 200, 300, but there's heat that's going in, this is temperature. And the curve will always look something like this. You'll have a solid, but notice what's happening. The solid's temperature is going up. For water, this is 0 degrees Celsius. Maybe this is negative 20. And then the temperature does not change. And then the liquid, which is right here, goes up to 100 degrees. And then it boils for a lot longer. And then it goes up after this. This is the three phases of matter. These are the phase changes. This is boiling if we're going this direction, and this is melting if we're going this direction with the amount of heat that goes in. Now, what we need to do is talk about what happens in here. And it's not something that you're surprised at. If you take a pot of water, put it on the stove, start putting heat in, or we do it over our Bunsen burner, what you're expecting is exactly what's going to happen. The temperature's going to rise. Well, how much does it rise? Well, the answer has to do with how much heat you put in and for how much heat you put in. And the what we have for every material is something called a specific heat capacity. Capacity is the idea of what it can hold, and it's specific to every single compound. So over here, I have three different compounds. I have lead, and there's a different specific heat capacity for each phase of matter, solid, liquid, and gas. Now with lead, I only have 0.16 joules grams degrees Celsius. Zinc is about twice as much, or actually closer to 2.5 times as much, 0.39. As a liquid, it's 0.501. And for water, we have for ice 2.02, which by the way is a lot bigger than those, 4.18 and 2.06. Now what does that unit mean? Here's what specific heat capacity does. It tells us how much heat is needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. All right, 1 gram of a substance by 1 degree Celsius. So let's take zinc as a solid. The specific heat for zinc as a solid is 0.39 joules grams degrees Celsius, and that's on the bottom. It's joules times grams degrees Celsius. Here's what that says. If you put 0.39 joules into zinc as a solid, its temperature, and you do that for 1 gram, its temperature will rise by 1 degrees Celsius. Okay. If I had 2 grams, I would have to put in twice as much heat to make it go up 1 degree Celsius. If I wanted to raise it 10 degrees Celsius, I would need 10 times this amount of heat. And heat and energy, again, are the same thing. So we actually have an equation that looks like this. And by the way, Cp, the specific heat capacity, for some reason is listed as Cp. It's a capital C with a lowercase p. And we mark whether it's solid, liquid, or gas. This will be the equation that we're going to work with. In fact, I'll write it over here. It will be that Q is equal to mass times the specific heat capacity, time the change in temperature. I don't know why I put that in parentheses, times the change in temperature. And the change in temperature can be in Celsius or Kelvin. You might think it would have to be in Kelvin, but it doesn't. So let's do an example problem. Let's say we had this problem, and you'll be asked to do these in the homework. How much heat is needed to raise the temperature of zinc from 20 degrees Celsius to 300 degrees Celsius. And we should have had the temperature of, let's put in 50 grams of zinc. All right, so my equation is that Q is mass times specific heat capacity times the change in temperature. Well, the mass is given to me, 50 grams. Specific heat capacity is something that will always be given, or we can look it up. You can go online and find this. 0.39 joules grams degrees Celsius. And then the question is, what's the change in temperature? Well, the change in temperature is from 300 to 200. We're looking for how much that changed. We would subtract, and this would be 280 degrees Celsius. So it turns out it wouldn't matter if you went from 30 degrees to 310 or from 50 to 350. It wouldn't make any difference. It's just what the change is. So 50 times 0.39 times 280 gives me 5,460 joules. Okay. And that is basically taking and saying we're going on zinc's curve. If we had a curve here for zinc, if we're down here starting at 20 degrees, and we would go all the way up here to 300 degrees, and zinc as a solid would keep on going. The question is, how much heat does it take through this time to get us there? How much heat? Well, it's this much, 5,460 joules. So that is the first part of this. Now we're going to put the two ideas together, but that is specific heat capacity and how you would do a problem. So let me show you a slightly more complicated problem. We're going to use water here, and you'll have a number of problems with water. Well, actually, let's use zinc again. Let's say that we had this. I want to raise the temperature. Let's keep it the same, 50 grams of zinc, but we're going to go from 20 degrees to 500 degrees. You say, oh, okay, this is real simple. I'm just going to do Q is 50 grams times 0.39 joules grams degrees Celsius times, this would be 480 degrees Celsius. The problem is if you do that, you will get the wrong answer, and here's why. Something important happens at 420 degrees, and this will be given to you as well. The melting point of zinc is 420 degrees. When it goes from at 420, we are going to have to go through a phase change, which we learned about last time. That would be Q is mass times heat of fusion. Notice there's no change in temperature on this because the temperature isn't changing when you are melting something. You're simply breaking the bonds. You're simply causing the molecules to stop being fixed together and now are able to move around. No change in temperature. But what's actually happening, if we look at this, is if I was to take zinc's curve, zinc, if we started down here at 20 degrees, will be a solid all the way to 420 degrees. And by the way, that'll always be given to you or able to be found out. And then it's going to melt, and then it's going to go up from there. So what we're interested in is how much heat does it take to go from here to here? Well, this is actually a three-step problem. We need to figure out what the heat is in this phase, how much heat is needed here, and how much heat is needed here. All right, well, what is this one? This would be Q is equal to the mass, which was 50 grams. Now watch. This is 420 minus 20. The change in temperature here is 400 degrees Celsius. 420 minus 20. And because it's a solid, the heat capacity is 0.39. I should write that nicer. 0.39 joules, grams, degrees Celsius. And 400 degrees Celsius. This is the heat for this section here. The heat for this section, I'm going to do it up here, is going to be mass times heat of fusion. And that would then be 50 grams times the heat of fusion was 112 joules per gram. And then finally, this little section here, by the way, this is going from 420 to 500. This is 80 degrees Celsius. This little section, I'm going to bring it down here, will be Q is equal to 50 grams times 0.501 joules, grams, degrees Celsius, times 80 degrees Celsius, okay? And I'm getting this number from 420 minus 20, that number, and this one is from 500 minus 420. And now we would put all of those parts together. So basically we're going to have a Q for what we're doing when we're raising the temperature of the solid. And that would be this one right here. So 50 times 0.39 times 400. And that would be 7,800 joules. And the Q for melting, the heat, 50 times 112. And that's 5,600 joules. Notice, it's almost as much to melt it as it did to raise it 480 degrees, or 400 degrees, not 480. And then finally, 50 times 0.501, times 0.501 times 80, and this is 2,800, or 2004, we'll just round it off to 2,000. And that would be then to raise the temperature of the liquid. And we would then add those together, 15,400 joules. So the amount of heat I have to put in is 15,400 joules. Now, the granddaddy problem would be with water, and you'll have some of these on your homework. So I'm going to do one problem real quick and set it up. And then there's a worksheet that goes with this. Again, you need to show me the work on the worksheet because I have the answers for you at the bottom. But let's take water. Water has a melting point of 0 and a boiling point of 100, and we need to know both of those. If we go through a phase change, we have to use this equation. And here's your heat of fusion, heat of vaporization, and for water, these are your specific heats for solid, liquid, and gas. So let's do this. Let's say we have, let's just make life more interesting here. We have 1 mole of water. By the way, 1 mole of water is 18 grams. And we're going to raise the temperature from negative 50 degrees Celsius to 190 degrees Celsius. So what we need to do is think through water's curve. It's going to start down here at negative 50. It's going to go up to 0. It's going to go from there to 100. It's going to boil, and then it's going to go up to 190. So we actually have 3 sections. We have these 3, which come from this equation, and we have these 2, which come from this equation. So the first thing I want to do is figure out what my change in temperatures are. So what I do is this. I go from negative 50 degrees to 0 degrees. It will be a solid. Let me move this over a little bit. Negative 50 degrees to 0 degrees Celsius. It's a solid. At 0 degrees, it melts. From 0 degrees to 100 degrees, it is a liquid. At 100 degrees, it melts. It boils. And from 100 degrees to 190 degrees, it is steam. This delta T right here is 50 degrees. No delta T here. Delta T here is 100 degrees. And delta T here is 90 degrees. And so now I can work each one of those three out. Q will be 18 grams times 2.02 joules grams degrees Celsius, that number right there, times 50 degrees Celsius. Q here is 18 grams times 334 joules per gram. Here, Q is 18 grams times 4.18 joules grams degrees Celsius. By the way, I did this wrong. It should be joules grams degrees Celsius times 100 degrees Celsius. And then Q here is 18 grams times 2,260 joules per gram. And finally, 18 grams times 2.06 grams degrees Celsius, and that went up 90 degrees Celsius. So, real quick, 18 times 2.02 times 50, no, times 8, yeah, times 50. And this is 1,000, I'm going to round it off, 1,800 joules. 18 times 334 is 6,000 joules. 18 times 4.18 times 100 is 7,500 joules. 18 times 22,600 is 41,000 joules. Notice, more heat here than all of that put together. It takes a lot of energy to boil away water. And then finally, 18 times 2.06 times 90. And this is 3,300. Again, I'm rounding off to two places. So finally, we would add all of those together. 1,800 plus 6,000 plus 7,500 plus 41,000 plus 3,300. And I think I've done that right. It's a little hard for me to see in this room. 59,600. So that is a little bit of math that goes with these problems, and you will be asked to do a worksheet. The worksheet, I think, is, it'll be posted under your lesson. I forget what I've called that worksheet. Well, let's just do it. It'll be 13.2. Heat needed to change temperature. Let's just call it that. And there'll be a worksheet there, and you'll be asked to do those problems. So, all right, one more video for this week, and we'll get to that as soon as I get to it. All right, we'll see you later. Hopefully we'll see you soon.